Let's pick up where we left off in the lab. You recall you did an experiment using AC waveforms where you had a 300 ohm resistor in series with a negative J 300 ohm capacitor. And we're going to drive that with 120 volts, 60 hertz in this case. Now, the total impedance is 300 minus J 300. The current may be calculated as 120 volts over 300 minus J 300, which is approximately equal to 280 milliamps at a phase angle of 45 degrees. Let's do a sanity check on this with Eli the Iceman. The angle is positive, so that means it is indeed a capacitive circuit. Now, the voltage on the capacitor can be calculated as a current by the impedance of the capacitor, which is our 280 milliamps by negative J 300, giving us approximately 85 volts at a phase angle of negative 45. The voltage on the resistor may be calculated as the current times the resistor. Which again is 280 milliamps at a phase angle of 45 degrees multiplied by 300, which gives us 85 at a phase angle of 45. Now, that's what we know from the lab. Oh, while we're at it, we may as well plot these out. So we have the real axis, the imaginary axis, at a phase angle of 45 degrees. We have 85 volts, and at a phase angle of negative 45 degrees, we have 85 volts. We can do a quick check with Kirchhoff's voltage law. So 85, phase angle 45, plus 85, phase angle negative 45, is approximately 120 volts, where we started from. Now we're going to shift over to Multisim and perform the same steps. So the first thing to do is open a new file, and then we're going to enter our schematic. So you start here with a voltage source. By default, it's 1 volt at 1 kilohertz. That's not what we want. We want the voltage to be 120 volts RMS, so we're going to set that to about 170. And then 60 hertz. Next, we're going to add our resistor and our capacitor. And then we rotate the capacitor once we have it set. Then wire them up. Notice the node notice how it labels the nodes. So there's node 1, node 2, and node 3. We add a ground. Now pay attention to what node 3 does. As soon as we connect up that ground, node 3 drops down to node 0. That'll be really important later on when we start adding our voltmeters to the circuit. Change the resistor to 300 and change the capacitor to 8.84 microfarads. And I'll leave it up to you to run the capacitive reactance formula for that one. To test it out, we're going to add an amp meter. Again, like we did before, we want to see if we can get 280 milliamps. The play button here runs the simulation. And you'll notice the numbers are bouncing all over the place. That's not what we wanted. So we're going to stop it. And over here on the right, we're going to change it to periodic instead of instantaneous. And when we do that, there's our 280 milliamps like we had before. Next, we're going to add some voltmeters. We add a voltmeter to node 2. Now we're going to give it and then we give it a name, and we'll call this the voltage on the capacitor, so V_capacitor. We'll add another voltmeter. We'll add it to node 1, and we'll call this voltage resistor. Actually, be careful though. It's really not voltage resistor. It's actually voltage resistor relative to ground. If we want to be fussy, we should go back and we should name our capacitor voltage capacitor with respect to ground. And if we run the simulation, oh, don't forget to put it back to periodic. All right, when we run the simulation, we should see 120 volts on node 1, and there's our 85 volts on node 2. If we want to measure the voltage across the resistor, what we need to do is we need to add a voltage reference. It's like moving the black wire on your voltmeter to a different point in the circuit. So we're going to add this reference, and we're going to call it node 2. Then we're going to go back to our voltage. Then we're going to go back to the first voltage meter we dropped down. And instead of having it referenced to ground, we're going to reference it to node 2. And then we'll change the name back to just voltage resistor. So that's more appropriate. That's what we're really measuring now. And we run it. And there it is. There's the 85 volts across the resistor, which is again really just node 1 to node 2. And there's the voltage across the capacitor, which is node 2 to the ground node. If you want, you can go ahead and view this with the grapher, which is just like an oscilloscope. If your oscilloscope's running, be sure to put it into normal mode on the right side there. Anyway, this here is the voltage on the resistor. And then with a 90-degree phase shift, we see the voltage on the capacitor. Again, that was a phase shift relative to each other. It might be interesting to go back and add one more voltmeter to this simulation. So we add this voltmeter here to the source, and we call it source voltage, and we measure it with respect to ground. Now when we run the simulation, there it is. There's our 120 volt RMS. Really quick, let's change the source of our trigger to the voltage source, and now we see that we have that 120 volts signal starting at phase angle 0. And you can see that the resistor is early by 45 degrees, and you see that the capacitor is late by 45 degrees.